So what are the various formulas that are used? The first formula is for power. Power is denoted by W dot. Its unit is watt. It is equal to mass flow rate of steam into blade speed into change in the whirl velocity. Okay. See, there is a plus or minus. When will you use plus? When will you use minus? Now, if CW1 is like this and CW2 is like that, then you use plus. Okay. If CW1 is on the left, CW2 is towards the right, or this is towards the right and that is towards the left. They are in opposite direction. Then you use a plus. Suppose they are in the same direction. This is CW1 and this is CW2. Their magnitude is not changing. The direction is same. Then you use a negative sign. Are you clear? So if the whirl component of velocity changes direction, this is in one direction, this is the opposite direction, then you have to use a plus sign. If in the velocity triangle you are given that CW1 and CW2 are in the same direction, then you use a negative sign. In all the formulas, wherever CW comes, there is a plus or minus. So the plus indicate, usually you get the plus case in a simple impulse turbine. When they are in opposite direction, you use plus. When they are in the same directions, you use a minus. So W dot equal to M dot U CW1 plus CW2. This will be the formula for power. Now, if I don't want it, the power in watt, I want in joule per kilogram, then it is specific work. You just divide the power by mass flow rate. You get small w. Then, two force formulas are there. The change in whirl velocity will create a tangential force on the blades. This force multiplied by velocity is giving the power. So the tangential force is the force that is driving the blade to whirl. So its formula is given by just m dot into change in whirl velocity. So the change in whirl velocity gives rise to a tangential force or a whirl force. Whereas the change in the flow velocity is going to give you an axial thrust on the blades. So this is bad. If the axial thrust is too high, then this is going to destroy the blades. This is good. Higher the tangential force, you will get a nice whirl. But if the axial thrust is very high, then there is a force that is pushing the blades in the axial direction. So this is anyway going to be present, but if we minimize this, then it's very good for the blades. Or this force should be little less when compared to the other force. Now, the next formula is efficiency for the blade. This efficiency is also called the diagram efficiency, meaning the velocity diagram efficiency, or it is called the blade efficiency, or it is called the turbine efficiency. In problems, you may be given in different names. Either it's called the blade efficiency, or diagram efficiency, or turbine efficiency. All mean the same thing. For an impulse turbine, the inlet energy is completely kinetic energy. And you know, kinetic energy is half m dot into c square. So this is the inlet energy, and the outlet energy is the work done by the rotor. So the inlet is, the fluid is coming at a velocity of Ca1. So its kinetic energy is half m Ca square. And the outlet of the turbine or the blade output is going to be the rotation of the blade or the power transmitted to the blade. So the output by input is going to be the efficiency. Now if you substitute the expression for W dot from here, M dot U CW1 plus or minus CW2, that M dot here will cancel with the denominator and you just get U CW1 plus CW2 by half Ca1 square. So this will be the expression for the blade efficiency. Now, there is a derivation, but we are skipping the derivation because we don't have time. Optimum blade speed ratio. That is to get the maximum efficiency. From this expression, we will take a derivative and set it to 0. The condition that the efficiency is a maximum. Then you get a condition that this ratio we call as rho. This is called the blade speed ratio. This is the ratio of the blade speed to the inlet jet velocity or the inlet fluid velocity. This ratio should be equal to cos alpha 1 by 2. A similar condition you would have even seen for a Pelton wheel turbine. Pelton wheel is an impulse turbine. Very similar condition you would have seen for a Pelton turbine. So I have skipped the derivation, but the optimum blade speed ratio, if it is given to be used, then we have to use U by Ca1 is equal to cos alpha 1 by